Swayam Prabha. Digital India. Educated India.
Hello all. So today we'll start a new topic regarding tsunami. So as in the previous class, I'm sure sir has taught about you some of the definition and concept regarding tsunami. This class will be all about tsunami modeling. If we talk about tsunami modeling, it means here we are going to simulate the tsunami in the form of its wave height, its travel time, means how much time it is taking to reach a coast where it has been, means from place of its generation towards the coastal areas nearby or some far, and on the basis of that it has been divided on near shore and far shore tsunami. So this modeling part helps in three ways. It helps in preparedness, it helps in formulating some mitigation measures, and then which in all about lower the risk, and this all can be grouped into what we call it making an hazard assessment map regarding the tsunami. So I'm sure sir has explained you about tsunami and some of the concepts behind it and definition, but to brush up we'll go with the, so first we will talk about what is tsunami. It's just only to brush up the knowledge so that we can move to modeling part and you can easily relate how we are coming to from tsunami, how we are modeling the tsunami. So what is tsunami? So tsunami is a Japanese word, in English translation means harbor wave, represented by two characters. Su means harbor and nami means wave, or it can also be called as a wave train or series of wave tsunami generated by earthquake. Means as sir has already talked about that tsunami can be generated through various sources. It can be from earthquake, it can be from volcanic eruption, or it can be from series of landslide or mega landslide in the submarine, in the underwater, in the ocean, or it can be by nearby explosion, and even costing body like meteoritic impact, which is a very rare case. It can also generate tsunami. So here is the schematic diagram of tsunami. This tsunami is generated by the earthquake, as you can see here, and after the earthquake the energy get released and it transport its energy in the water lying above the water column, and it generates the wave, and this wave travels towards the coastal areas and forms the tsunami wave. So here we will talk about the tectonic activity leading to generation of tsunami. As in the previous slide we have seen how the earthquake has created tsunami. This is some of the generalized part. As you can see here, slab is subducting and one slab is overriding it, and when there is an earthquake it generates the tsunami, and these are the steps how a tsunami gets generated. Means as you can see, the North American plate is the overriding plate on the Pacific plate. The deformation, and here the deformation is taking place between these two plates, which is causing stress. If there is a high stress leading to the slip, then that slip will turn into a form of energy which will create the earthquake, and that earthquake occur as a snaps back, which generates the energy and is transported into the water, which creates the waves. These are the high stress zone at plate boundary where the earthquake and then tsunami are generated. So here is the map of the world, where we can see the tsunami prone areas, which is this, as you can see the subduction zone where where it has the potential of generating tsunami, of course by volcanic eruption or the earthquake or maybe both. Here is our Arakan Andaman Sumatra subduction zone, where we have experienced recently 2004 Indian Ocean tsunami, the most devastating one after the 1960 Chilean earthquake and tsunami. Here are the subduction zones which has the potential of creating or generating the tsunami: the Chilean subduction zone, the Colombian Ecuador, the Puerto Rico subduction zone, the Kamchatka subduction zone. So, as already told you about Sumatra Andaman, and above it is Arakan. So, these are the subduction zone which has the potential of generating tsunami. And as I was talking about some near shore and far shore tsunami. So, as we have seen in the 2004 got generated near the Indonesia, the epicenter was Band Aceh. It was a far shore tsunami for the our Indian subcontinent. Okay, but if that kind of earthquake would have happened near the Andaman area, then the devastation would be more than what we have seen in 2004. So, in the form we were somehow about lucky that the epicenter was far away from Indian subcontinent, but not as lucky as deformation is still happening in this area, and we can expect an earthquake and mega tsunami in near future. So, in this we will talk about global tsunami and percentage of different type of generation mechanism. Means, as I have already told, that tsunamis can be generated from different sources. It can be from earthquake, it can be from volcanic eruption, it can be from series of landslides. So, in this diagram you can see it is showing the distribution of tsunami around the world. The area which is experiencing more amount of tsunami, it has been shown here. So, you can see the 70% is held by the Pacific Ocean. In that Pacific Ocean comes the Japan, South Pacific Islands, North and Central America, South America, Russian Federation, Asia, in which our Indian subcontinent, Indonesia and other countries in the Southeast Asia comes, which is already Indonesia. So, and Alaska and Hawaii, and other 6% is by the Indian Ocean, 9% by the Caribbean Sea and Atlantic. Means this area experience less number of tsunami than the Pacific Ocean. Now, here is the diagram. You can see the mechanism from which tsunami can be generated, and as you can see, the most of it is constituted by the earthquake. 81% of tsunami are generated by the earthquake. Then we can 6% is constituted by our earthquake generated landslide, as and then 5% is by volcanic eruption. As we can see in the recent Anak Krakatau volcanic eruption has generated tsunami due to the after the volcanic eruption series of landslides occurred in that area, which generated the tsunami in the nearby countries or the areas, and the 4% is constituted only by the landslide and 4% by the other sources, for example meteoritic impact and some other mechanisms. So, here comes the tsunami modeling part. So, after getting the concept of tsunami and definition of some of the tsunami related words, here we come to the modeling part. As I have already explained in the start, the modeling is nowadays very means it is the need of time, so that we can lower the risk by having a well preparedness, by having some mitigation measures, and on all that we can prepare a hazard assessment map for the area. So, as you can see here, as you can see that it is difficult to predict the timing of tsunami arrivals and their devastating nature. So, here comes the modeling part. Means we can't predict when it is coming, but from the model we can lower the risk. Means where it going to be tsunami, where it going to be very much effective or where it is very less effective, those areas can be categorized, and on that basis we can lower the risk in that area. However, with the study of tsunami deposits and its modeling can generate a hazard assessment map. Though these studies, one can analyze the impact and the nature of tsunami-genic waves. So, from these studies, what we can analyze means how the past tsunamis has behaved, what was its wave height, how much time it has taken to reach the coast, and what was the inundation, how much it has inundated in the coastal areas. On the basis of that, we can prepare an hazard assessment map, and we can demarcate those areas as a tsunami prone areas where no construction should be allowed, or very means restrict construction should be allowed in those places. This helps in formulation, design, upgradation of mitigation measures with the early warning systems. So, here comes the objective why we need to model the tsunami. Simulation of tsunami genic waves to generate the amplitude and travel time maps. As I am simultaneously just saying that we need to generate the amplitude, the wave height and the travel time maps. So, it is from this modeling part we generate those parameters, which is very helpful in our in order to study the tsunami. Interpretation of generated results to know the severity of impact at desired locations. When the location which are near to the tsunami source, which are near to the subduction zone, which are prone to earthquake and then generated tsunami, it can be demarcated and we can lower the risk in those areas. To see means if Arakan Andaman means as a people, as we are living in the Indian subcontinent, so we need to study this subduction zone, that Arakan Andaman and also the Sumatra zone, as it is capable of creating big tsunami event, which we have already seen in 2004. So, here I am going to get into some of the case study which I personally have carried out in my lab, and I am going to show some results that how I have generated the tsunami waves, the travel time maps, and will interpret on the basis of those that how much our east coast of India is prone to tsunami, and it is need of time because because we are the developing country, population is at very fast rate, and so we need to study this and we need to prepare some hazard assessment map of that area, so that the risk from the tsunami, the devastation from the tsunami can be checked, the risk can be reduced. So, this is the map which shows the Arakan part, the Andaman part and the Sumatra part. This is the subduction zone which is in some arcuate in nature, and here is the epicenter of 2004 Indian Ocean tsunami, and few more tsunami has also been marked here. Here, as you can see, this is the 1881 tsunami, this is the 1679 tsunami, and this is the Arakan tsunami of 1762. This 1762 tsunami was underestimated, and later it has been studied by Cummins, which we will discuss in the following slide. So, as you can see, series of tsunami events has occurred, and how much we are our east coast of India is prone to these events. We have very less information, observable information or the model information of this tsunami, that what they have caused at that time, the kind of devastation they have caused in this region, in our east coast of India. So, I am trying to study and I am trying to come up with some hazard assessment map of this area, so that ultimately we can check those events, the tsunami which are coming, and we can lower the risk in this area. So, what methodology I adopted for the modeling part is that to simulate the tsunami, I used the software Nami Dance. The version was 5.88. It requires, to generate the tsunami, first we require is the bathymetry map and the topography map, topography data sets. This bathymetry map I downloaded from JEPCO, and this topography data set I downloaded from Earth Explorer USGS. As item data have been used in this model data. So, it requires bathymetry and topography data sets of the region along with the rupture parameters as the input file. So, first we input these two files in our Namidas software, and then we generate the rupture file. The first, that is the first wave which occurred during the volcanic eruption induced landslide or the earthquake. So, here are some snapshots from that software Nami Dance. So, what we first do is to input the bathymetry information. Bathymetry information means the information about the area in which you are working. I am working in the Andaman Arakan Sumatra part. So, I will give the lat long of that area, and then I will get the first rupture wave of that area, and that rupture wave will be act as a source file in the generation of other initial waves or the wave train of the tsunami due to this earthquake or the landslide. So, we take the SRTM data and the JEPCO data in the first part, then we input the rupture data what we have generated from here, and then we set the grid which is 800 here, and then we give the parameters, the fault parameters. Here the strike angle of the fault has been given, which is 315, then the focal depth in kilometer, which is 10, and the fault length, the length of the fault which I have given here around 700 kilometer. The width of the fault is given is 150 kilometer, and the other parameters regarding fault is dip angle which is 10 degree, then rake angle which is 110, then the displacement, how much displacement has been taken during the earthquake which at last generated the tsunami. It is about 10 meter. When we do all these things, then it takes around 4 to 6 hours of simulation, and the first what we get is this wave. As you can see, this is our first wave which generated during the tsunami, and then we generate a series of files after giving the fault parameters, which is the fault length, fault width, focal depth, the strike of the fault, dip angle, rake angle, displacement of the fault, which is about 10 meter in this area, that is Andaman Sumatra, which was here was the epicenter of that earthquake, and this is the rupture created by this earthquake which was around 1300 kilometer. So, we gave those parameters and generated the tsunami in this whole area, and we see how much time it has taken to reach this part, east coastal part of India. So, as I have told that we are simulating to the 2004 Indian Ocean tsunami. So, this was the tsunami which got generated during the 2004 Indian Ocean earthquake, regenerating the condition of 2004 tsunami having 1100 kilometer or 1300 kilometer fault length and 150 kilometer width of the fault that ruptured at an angle of 329. These are the fault parameters which I have given in the Namidown software to generate this tsunami, and you can see the wave height of this tsunami in the Indian Ocean was way more. It was around 3 to 4 meters in this area, which was the epicenter of the 2004 Indian Ocean tsunami. And the Indian subcontinent, you can see it was around 2 to 3 meters. This part received the tsunami of 2 to 3 meters, and it depends on the high and low tide condition also. This is the height of the tsunami wave, but if it came around the high tide condition, then that can reach up to tens of meter and can create much more devastation in this area, in the Indian east part of the Indian subcontinent. So, here is the time chart of the Indian Ocean tsunami of 2004. So, as you can see, it took around 180 minutes or around 150 minutes to reach the Indian Ocean part, but only 10 to 20 minutes it takes to reach the epicentral position, that is in Indonesia. So, after modeling the data, what we have done, we have the observed parameters of this 2004 Indian Ocean tsunami. So, we need to validate our model data. So, what we have done is that we have compared the travel time comparison between the obtained values and the observed values. So, as you can see, these are the gauge stations which we need to put in the modeling part. So, as you can see, Chennai, Port Blair, Paradip and Visakhapatnam. So, in Chennai, the tsunami, the observed time was 2 hours 34 minutes, but the model part gave us around 1 hour 54 minutes. So, this kind of differences are coming because the model data did not take the account of the geomorphology or the coastal morphology of that area, as it changes from place to place. So, it is approximating those things. So, we need to just verify those errors. So, we can't get the actual numbers, but near to that value we can get from the model data. So, as you can see, around 2 hours, 2.5 hours it is taking to reach in the observed part, but what we have computed, it's around 2 hours. So, only 30-minute around information kind of error we are getting. So, that we can input in our hazard assessment map, whereas in Port Blair it was, we find that only 5-minute difference was there between the observed data and the computed data. And here is the Paradip and Visakhapatnam. So, from here we can see that near about our model data is kind of giving the near about results which was observed during the Indian Ocean tsunami of 2004. So, this was the run up height which we called as the wave height that struck the east coast of India and Andaman part. So, after computing the travel time comparison map, we computed the run up height, the wave height of the tsunami which struck the east coast of India and Andaman part. So, as you can see, the Chennai, Port Blair, Paradip and Visakhapatnam are the gauge point location for our model data, and the observed height was around 3.2 meter in Chennai and the computed height was around 2.46 meter, means it is near about same, and the Port Blair experienced 3.5 meter, the computed was 2.9, Paradip the observed was 3.2 meter and the computed was 2.6, Visakhapatnam 2.9 and the computed was 2.37. So, near about our wave height of the model data is also corroborating with the observed data of the Indian Ocean tsunami of 2004. So, as now our model data is validated, we can use this modeling, or we can use this parameters to generate few more tsunami which has occurred in that area, as I have shown that the 1762 tsunami, the 1881 tsunami and other tsunami in anywhere in the world after validating our modeling part. So, as I have already told you that there was an underestimation of tsunami of 1762, the Arakan tsunami of 1762. So, there was a paper in Nature by Cummins which carried out this study of this 1762 Arakan tsunami, and he come up with that firstly the authors were on the basis of observed data were saying that there are small island Ramari. They said that rupture after the 1762 earthquake in this area, rupture was only up to this far, but other observation from the inland of the Bangladesh near the Dhaka and Kolkata, they say that they have experienced, means the observation of people at that time, it was that they have experienced the tsunami wave up to upward in the upstream part of the Padma river up to the Dhaka or Chittagong part and somewhere near the Kolkata. So, he thought that might be this earthquake was underestimated. The rupture length was way more than it has been observed, that it has been manuscripted. So, he modeled that data and has generated the tsunami wave. As you can see that the Indian part has experienced up to 2 meter of wave during the 1762 earthquake and tsunami generation of Arakan. So, with this modeling part we can recheck the paleo tsunamis and come up with some more information which has been not manuscripted at that time. So, the modeling part is very important in the study of tsunami, and with that we can, what we can do is that we can prepare some hazard assessment maps. In that we can demarcate those areas where the tsunami can come, and we can give the authority some information about that these areas can be allowed for construction or any other anthropogenic activity. So, now the conclusion. So, as in India we are seeing the exponential growth in population and infrastructure development. So, this kind of modeling is need of time. Lack of understanding on hazards, as you can see the underestimation of 1762 tsunami that has been recalibrated, restudied by humans. The level of risk has increased in the last few decades with the exponential growth in population and the infrastructure development. Detailed study with different approaches need of time, means which, and that different approach is can be tsunami modeling or the study of the tsunami deposits. I am sure sir has taught you. And then comes the prediction. However, the prediction is difficult, but continuous real time monitoring can be carried out, and that can be used in the modeling part, and we can further improve our model data. Then comes the preparation of tsunami hazard assessment map, which I am saying again and again, and with this we can come up with some maximum height and inundation, so that it can give a solid ground to our hazard assessment map, and we can give this information to our authorities, so that the risk, means we can't totally eradicate the hazard, but we can lower the risk. So, after this I am sure that you will know how the modeling part is very important, and with this we can help in many other ways to reduce the hazard. Thank you.